In section 6.5, we want to apply calculus to a different kind of problem, yet another one that we could not solve until calculus was invented. Namely, we want to know the lengths of curves. Now let's talk about what the arc length of a function is. So when you're in algebra class, if you're given 2 points and a straight line between the two, you know that distance, right? That we had a formula for distance. It involved the change in x and the change in y, and so on, right? All right. But what if we want to know the distance along a function? Same 2 points, but it's curvy between the two. How would I find it then? Okay, so arc length then is the distance along the curve. So if you could imagine, if I could stretch that bendy curve out into a straight line, how long would it be? So it's distance along the curve. Now, technically, the method we come up with should be able to work for straight lines, but it's difficult to measure, so it should work for straight lines too, trivially. But we're particularly interested in curvy lines, non-straight lines, different lines also. But we're interested in curves, right? Curves that don't play nice. Now there is one curve that we actually know how to work with. So if we know how to do straight lines from algebra, there's one curve that we know how to deal with, and that's a circle. A circle, of course, has been known about and worked with as a geometrical object since, well, the ancient Greeks at the very least, but of course circles around before that, but the mathematical formulas were begun by the ancient Greeks. So we know how to find the area, or excuse me, the length of an arc along the circle right here. And we call that arc length. The arc, oops, sorry, that was an equal sign. S is equal to the arc length. Okay, and it's that arc length is equal to the radius times the angle that is swept out, right? We learn that formula in pre-calc and trigonometry because it's the foundation for what radian measure is. Of course, that angle theta must be in radians. Right? So S is equal to r theta, where theta is the angle swept by the arc. In radian measure, of course. I mean, radians aren't really even a measure. They just are, right? This is how they're defined. So, and then r is the radius. And then S is the arc length. There, it was bothering me. Radians aren't a measure, radians just are. So this is what a radian is. So the theta angle is the arc length divided by the radius. Right? It's how many radii, if you will, would fit into that arc. All right, now that's great for circles. I mean, we know these from pre-calc, right? So we can deal with these from pre-calc, no problem. And we can do straight lines. But how do we do it for any old curve? Just any curve. Well, what we can do is we can kind of use this little trick where we zoom in a lot. Let me show you on a Desmos graph really quickly. So if I take this curve, which obviously is curved, but then if I zoom in so that I'm very close to that curve, then more or less in any little zone, it looks like a straight line, right? So that's what we're going to do. We're going to kind of use that trick of zooming for the sake of, well, being able to figure out a formula. Now, so if we zoom in and that curve looks pretty close to linear, I mean, it's not perfect. You can see there's a little bit of arc or arch, whichever one you want to say, above that line. Well, then we can kind of approximate that ds, by the way, S stands for secant. If you remember, a secant is a straight line that cuts across a curve. So the S is for secant. the secant of a curve. Oop, my n doesn't have enough. There we go. Secant. Right? That's what that means right there. So when you cut across a curve with a straight line, that's called a secant. So this should be true. ds squared, because of the Pythagorean theorem, of course, let me say it, dx squared plus dy squared is equal to ds squared. Right? Hello, Pythagoras. Such a useful theorem, used all the time. All right, now I know we want to kind of head to a formula for ds, but I want to kind of work on this a little bit first. So what I'm going to do is I'm going to divide everything by ds squared, or dx squared, excuse me. Why? Well, because I can. I mean, there's nothing stopping me, right? So this is true, right? This equation, it's totally true. But then I can go a little step further and I can say, okay, if I take dx squared plus dy squared equals ds squared, and I divide everything, all three pieces, by dx squared. Right? Okay, then what would that be? That would be, well, 1 for that first term. 1 plus dy divided by dx squared equals ds. Well, I'm going to leave this one, ds squared over dx squared, because I'm going for something here. I'm actually kind of blending these two parts together. All right, so then, if this is true, I want to solve this for ds. So I'm going to get ds by itself. So I'm going to do myself a favor and multiply both sides by dx squared. I know I just divided it in, but I can do whatever I want. So I'm going to divide, or I'm going to multiply. But I multiply this whole side by dx squared, like that. Okay, so over here, it's going to cancel and divide away because dx squared and dx squared is gone. And that leaves me ds squared is equal to all of this, right? So I'm going to flip it around. So ds squared is equal to 1 plus dy over dx squared. I'm not going to distribute. I'm going for something here, times dx squared. Now to make ds by itself, because that's what I want a formula for ds. So to do that, I'm going to take the square root of both sides, everything on both sides. So the square root of ds squared will be ds, this is looking promising, equals the square root of 1 plus dy over dx squared. And then the square root of dx squared would just be dx. Interesting. So then, what if I want s? How would I find it? Well, I have a differential here. This is looking familiar, because what you're going to do is you're going to integrate both sides. The integral of ds will be s, right? Because that's 1, right? And you're integrating with respect to s. So the integral of 1 with respect to s is s, which is equal to the integral of the square root of 1 plus dy divided by dx squared. And there you go. You've actually just found the formula for arc length. So I proved to you that the formula that's on the next page is going to work. Clever, huh? All right, and it's all by zooming in and using the zoom in trick. Now think about this. What we're going to do is, of course, we're going to stack lots and lots of them. So it's not really just going to be one, teeny tiny section of the curve, but you're adding up all of them. And I actually have a picture in the notes that's of that, but even better, I have it in Desmos, of course. So let me pull up my Desmos graph. And it's kind of similar to Riemann sums. What you're doing is you're starting off with this curve and you want to know the distance along the curve. And so each one of these sections can get figured out with the Pythagorean theorem, right? So the dx squared plus dy squared, etc. But what you do is you let the number of your segments get larger and larger and larger. So if I do that, then what's going to happen is, well, here, let's see. Let me let go to 15, right? Or let me go to here. Sorry, I'm trying to get my slider bar back. There it goes. So 18, 20. Do you see what's happening? So even at 24, look how close those purple little line segments are, right? If I zoom in, you can kind of see, oh, there it is, right? But if I zoom out, right, it's better and better, right? And then of course, if I let n get larger and larger, say it goes to infinity, then that purple line segment piece will actually perfectly match the curve. And I can let it go even larger. There you go. That's at 50. Look how close those curves are at 50. I have to zoom in a lot in order to show a gap between them. If I zoom back out, you can see how well they match. So it's similar to Riemann sums in that we're taking the limit as n goes to infinity, but it's not adding up rectangles. What we're doing is adding the sections of each of these. So each of these little sections is being added up. And we add them and add them and add them, and we let the number of them go to infinity, right? So each of these is a little ds section. And then we let the number of them go to infinity, which makes them infinitesimally short, which means that this formula will work. Beautiful. And of course, there's an analogous form if in case we're working with respect to y. If this was a function with respect to y instead of respect to x, it will all work the same way. Now there are, sorry, that was a typo. There are two major caveats to this definition. Continuity and cusps, right? So the curve must be smooth over the domain. Now, not the little purple parts, because those by definition aren't smooth, right? We're taking a finite number of them originally to think about it, but then we're actually letting it go to infinity for each of the number of segments. But it'll only work if the curve is smooth, and the curve must be continuous. So I guess I'll just put that up here. Continuity with no cusps. Cusps are sharp points like that in a graph, right? We can't have that. Some books call them cusps. Some books just say they're sharp points. You can't have them, so it doesn't make any difference. All right, so it must be smooth, right? Smooth and with no cusp, and it has to be over the entire domain, and the derivative must exist. So to be smooth, it has no cusps, and it has to be continuous. And to be, the derivative must exist. So it has to, again, have no cusps and be continuous. I mean, that's kind of what this is saying here. So the derivative of x or the derivative of y, depending on which function. So f prime of x or g prime of y must exist. Right? Can't have any asymptotes. You can't have any sharp points. Now keep in mind that the arc length will actually never be negative. It cannot be, because we're taking the square root of something, and it's the positive square root at that. So, and then we're just adding them up. So there's no way this is going to be negative, right? It has to always be positive. It could technically be 0 if you were doing a trivial example, but arc length will always be positive because it's always distance, and distance is always positive, not displacement. Displacement is distance with the direction, but distance must always be positive. Now, this integral looks simple, but it is often actually quite tricky to do. So it is very common that we will have you set it up, and then we will use decimal approximations a lot for this one. If it can't be done with the basic integrals, just use Desmos. There are other ways to do some of these, which we'll learn in chapter 8. So we'll learn a few more integration techniques in chapter 7 and 8. But for now, if you can't do it by hand exactly, if the problem doesn't ask for it exactly, then just assume you're using Desmos. So give the setup and use Desmos. Now, if it does ask for it exactly, then you have to do it by hand. So if the problem asks for an exact answer, do the analytical work. You can always check yourself with Desmos. Nobody's stopping you, Matter of fact, I expect you to check yourself with Desmos all the time for every problem.